formalize the idea of hypothesis testing. So what is a hypothesis? So a hypothesis is a claim about a statement, is a claim or a statement about a parameter or a population, okay? A parameter of a population. So our claim about Jill was that she was a mind reader, okay? That's a hypothesis. Usually, a hypothesis is based on knowledge of a sample, okay? So we took a sample that proved Jill was a mind reader. So in hypothesis testing, we usually want to determine if some treatment had an effect on a population, okay? We're looking for a change in the characteristics of a population. So a good example is if students' reading scores increase when students play recorded music while they read, we say that the recorded music had an effect on students' reading scores. And this is something that's actually been proven to be true. So, in hypothesis testing, one wishes to show that real effect have occurred, right? We want to prove that the music helped the children read. We want to help their reading scores improve. We want to know that this didn't occur by chance. In order to do this, first thing we have to do is state a null hypothesis. The null hypothesis, which will be denoted H naught, that's how you say it, H sub 0 is H naught. The null hypothesis states there were no real effects. So our null hypothesis for Jill would be that she's not a mind reader. So that would mean the probability of her getting a selection right would have been 1 out of 5, so 0.2, okay? This is the opposite of what you really want to believe is true when we're looking for some real effects. We really wanted to prove Jill was a mind reader. So we've got two hypotheses. We've got our null hypothesis and we've got our alternate hypothesis. That's labeled H sub 1 or HA. This is the notation I typically use. So my alternate hypothesis for Jill, my null hypothesis was that the probability is equal to 0.2, right? So that's 1 out of 5 because we had like a star and a square and a moon and a circle and I don't remember what the other shape was. The triangle? Okay, so we thought if she wasn't a mind reader, she would get the card selection right 1 out of 5 times. So that means Jill is just guessing. If the proportion she gets correct is greater than 0.5, right, that means Jill is possibly not guessing, she's reading our minds. So our alternate hypothesis in this case would be the probability is going to be greater than 0.2. And we did our study and we found that the probability of her choosing it correctly was 50%. So, the original claim could be reflected in either H0 or H1 depending upon how the claim is worded. What does that mean? Okay? No matter what the original claim is, regardless of whether we're looking at, say, population means or population proportions, we're always going to form an H0 and an alternate hypothesis or an H1. Okay? We always want to assume H0 is true when performing a hypothesis test. So, how do we form our H0 and our H sub 1 or alternate hypothesis? Okay, so first off, we need to identify the claim we're going to be tested and write it out symbolically. So you want to make sure you identify whether you're working with a mean or a population proportion. Then we want to give the symbolic form that is just the opposite of the claim above, okay? H1 is the one that does not contain any kind of equality at all. H0 always has an equals sign. Depending upon the claim, H1 can be less than, greater than, or not equal to, okay? Like I said, H0 always has an equal sign. And keep in mind, these statements, are, like I said, are about the population proportion or the population mean. So let's work through an example. So I claim that the mean of IQ students is at least 120. Okay? because I said at least, okay, it always has this equals part, this equality. So I say the mean of students is going to be greater than or equal to 110. This means at least, right? That means my alternate hypothesis is that the mean of students will be less than 110. So I need to take a sample and I need to study this. Next, the percentage of men who watch golf on TV is not 70%. Okay? This is my claim. So I have an is not equal to, and I have a population proportion equals 70%. So the opposite of the above statement. This becomes our null hypothesis. So our population proportion equals 70%, and it's up to us to find a sample to either prove to reject or not reject, which we'll talk about in a little bit, H1. So here would be the population is not 70%. So here are some words we need to talk about. Sorry. A test statistic, right? That's when we take our sample. Critical values and critical regions. Critical values, these are also z-scores. And we're going to take a look at that in just a second. Well, sometimes they're t-scores too. So, a test statistic is the number you compute from taking your sample, period, right? Our test statistic with Jill was 0.5, right? She got the answers right 50% or 0.5 of the time. We use this information to either reject or not reject our null hypothesis. Notice I say reject or not reject. There is no accepting of your alternate hypothesis, right? There's only rejecting or not rejecting our null hypothesis, okay? We can calculate different test statistics. It depends on whether we're looking at means, proportions, etc., okay? And what this test statistic does is it'll tell you how many standard deviations away you are from the population mean proportion or standard deviation when you're looking at variance. Sometimes you're going to find a z-score, sometimes a t-score, and possibly even an F test statistic. We'll talk about that more in a little bit. It all depends on the population parameter you are investigating. So, if you're performing a test of means, and it's based on sigma being known, right, that's one of our requirements, then we're going to use a z-test. If our sigma is unknown, we're going to compute a t-test. That's why I had us on the last exam identify when we would need to use a z-test versus a t-test. And if you're still having some questions about that, there is a video exclusively on determining whether to use a z-test or a t-test. So, the test statistic is compared to a critical value, okay? The critical value separates numbers along the horizontal axis of the appropriate curve, it's always going to be a normal curve, into two distinct parts, a critical region and a non-critical region. So if I had a critical value of negative 1.96, it could be the case that this is my non-critical region and this is my critical region. Okay. So our critical region is the region that would cause H naught to be rejected, and the critical region is the set of those that would cause the H naught to be rejected from those that would cause H naught to not be rejected. You can have either one critical region or two, depending upon whether we're making a one-tailed or a two-tailed test. And we'll talk about that later on. But just to clarify some things. Tails refers to the ends of our normal curve, right? So here I have my left tail, here I have my right tail. Left tail would be for, say, mean is less than some given proportion. Right would be for mean is greater than, mean is less than, mean is greater than, I need an eraser. Mean is less than, mean is greater than, or if I have both, then I have a don't equal sign. So mean doesn't equal some constant. And we're going to cover all of this and do quite a few examples, so don't you worry. Critical values, alpha, right? That's the level that's been predetermined, and it's going to be 0.05 if not specifically stated. Remember we went over these in the last chapter, how the confidence level plus alpha equals 1. So our alphas are only going to be 0.05, 0.10, or 0.01. Those are our only options, and they're critical values, z-scores related to these areas under the normal curve. Okay, you're going to have only one critical value if you're conducting a one-tailed test. That's going to be left or right. And you'll have two critical values if you're conducting a two-tailed test. Okay. Another term for alpha level is significance level. Okay, how significant is what we're proving, right? When we proved that Jill had a 0.0089 likelihood of getting a 0.5 score by chance, right? We proved that it was statistically significant at not only the 0.05 but the 0.01 level, because this value is less than 0.01. So that would allow us to reject our null hypothesis. So if you have an alpha level of 0.05 and determine you should reject your H naught, okay, you could have an incorrect conclusion. The probability that you're making a mistake is 0.50, and it'd be a type 1 error. So again, here's our critical region. We have the set of all values of the test that would cause the rejection of H naught, okay, and it depends on our alpha, this critical value. And here we have our non-critical region. This would allow us to not reject our null hypothesis. Okay, so like I said, if it's a left-tailed test, it's going to be for less than, right? This would be a left-tailed test. A right-tailed test is going to be for greater than. Our critical region would then be in the right tail. And then a two-tailed test would be a not equal. Remember, this could also be a proportion if we wanted. And that means we have two critical values. So I need to know the area in both. But remember, the normal curve is symmetrical, so I can just take the area in 1 times 2. So how do I tell if it's two-tailed? Okay, this is when I have mu doesn't equal some number, or our proportion doesn't equal some decimal, right? Then we have two critical values, and we call that a two-tailed test. It's going to be one-tailed. Wow, I'm very redundant. It's going to be one-tailed if mu is less than some number, or p is less than some decimal, right? And it's going to be right-tailed if I have a greater than symbol, okay? We only have one critical value, one critical region. This could also be a proportion. I want to make sure you guys remember that we can do hypothesis testing for population means and population proportions.